Hi, and welcome to Lecture 5, in which we're going to start talking about energy. Now, energy is a notion that you've probably encountered in introductory physics as well as just out there in the world, and I want to give a sort of different take than maybe what you've seen before. In particular, I want to talk about why energy is useful when we're doing the kinds of quantitative calculations that we're focusing on so much in this course. So, the one thing that's really clearly true about energy from the first time that we encounter it is that energy is a scalar quantity in all of its different forms. Whereas most of the kinds of equations that we've been dealing with so far in this course are vector equations. Scalar real numbers have a number of nice properties that vectors don't have. The most obvious of these is that scalar quantities are ordered. I can say whether or not one scalar quantity is bigger than another, so 2.5 is bigger than 0.8. But I can't do the same thing for two vectors. In fact, to do so would require me to define what mathematicians would call a discontinuous map. So at least if I'm going to do it, I can't do it in a nice way. This means that if we can use some sort of scalar quantity to define our motion, or at least to describe our motion, we have some hope of being able to say that certain points in an object's trajectory, for instance, are characterized by some quantity which goes up and down, and we can say how much it went up and down over time. Okay, so that's just a little bit of background into why we might be trying to go the direction that we are, trying to describe our motion as much as possible using scalar quantities. We'll end up talking much more about this sort of approach when we get to Hamiltonian mechanics much later in the course. For now, we're just going to start diving in to some of the concepts that you're probably familiar with from an introductory course. The first of these is kinetic energy. So the kinetic energy, here we go, and this is a definition. We'll say that T is equal to 1/2 m, the absolute value or the magnitude of the velocity vector squared. Hopefully not too new for any of you. And of course, we've worked with this quantity before in a 100 level physics class, but we need to start to maybe take a more formal approach to thinking about it. And we'll do that right away by looking at the derivative of t with respect to time. So let's do that right away. Take a time derivative. Okay. So I'll have that t dot is equal to 1/2 and m are, well, they're just scalar constants, so they go right through the derivative. And now I'm going to re-express this in a different way. So let me put my d dt in here, and I'll express the magnitude of the velocity squared instead by saying that this is the dot product of r dot with itself. Now I know what to do with this. I can just use the product rule. All of the vector products, the dot product, cross product, all obey the product rule. So we're all good there. So this is going to be 1/2 m times r double dot r dot plus r dot r double dot. But the dot product is commutative. So this is in fact just going to cancel the half here. We'll just get m r dot r double dot. Okay. So where can I go from here? Well, I could say, for instance, that this is equal to the velocity dotted with m times r double dot, but that is the force on the object. All right, so that's pretty interesting. Now, where can I go from here? I think the direction that I want to go right now is to think about what happens when we move along the trajectory of an object. So let's draw in the trajectory of an object here. Okay, so this is the object's path, r. This is the trajectory. And let me say that this is r of t initial, and this is r of t final. And so what my equation is sort of suggesting that I want to do is look at what happens as I integrate, or sorry, as I look at the force along this trajectory. So I look at the force at every point. Okay, well, let me begin by doing what I just sort of spilled the beans that I was going to do and integrate this quantity. Now, I know by the fundamental theorem of calculus what I should get if I integrate this between two times. Okay, so I'll go from ti to tf, and I'll take the integral of t dot dt. By the fundamental theorem of calculus, this just gives me the difference in t between these two times. So t final, sorry, the kinetic energy at t final minus the kinetic energy at t initial. There we go. But I can use my formula here to look at this in a different way. So let me now use, let's call this star, to replace the integrand. So this means that this is equal to ti to tf, or I should say the integral from ti to tf, of, I'm going to reverse the order here, f dot r dot dt. Okay. Now, using a formula from vector calculus, I want to recognize that this is related to, in fact, closely related to, the line integral. So let me just carve out a little bit of space down here. If I want to take the line integral of a vector field, I would say that the line integral over the image of a curve C of a vector field V dot dr is equal to the integral from the beginning point of C in time, so let me call that ti, to the end point of C in time, tf, of v of r of t dot, and I didn't quite give myself enough space here, r dot of t. So again, C is the image of r on ti to tf. Great. Didn't get my dt in there. But that's exactly what we have up here. So this thing is just the line integral over this curve C of f dot dr. Good. And let's remember what the line integral is really telling us. It says that as I go along my curve, more or less, I want to add up all the little infinitesimal effects of forces that happen at each point along the curve. Great. Okay, so because this object on the far right-hand side has some relationship to this object here, I want to define this object. So I'm going to say, by definition, this thing is going to be what's called the work along the path C. So this is called where W is called the work. All right. An interesting point is that W depends on the image of the path C. In other words, the shape of this curve in Rn. But it doesn't depend exactly on the trajectory, in the sense that if two trajectories follow the same curve, then this path C, this image C, will be the same for both of them. And so the line integral of f along those paths will be the same. Another thing that's very interesting about the work is that if we have two forces, so if I have an object that's subject to two different forces, let's say F1 and F2, even though both forces determine the motion, we can define the work on each of them. So I could define, can define W1 on this path C to be equal to the integral from Ti to Tf. And in fact, let me drop that notation and just use the C notation. The integral along that path, image C of F1 dot dr, and W2 of C to be equal to the line integral along this image of F2 dot dr. Now, it must be the case that the net work done is the sum of these two quantities. But what's interesting is that even though the net force is the thing which defines the trajectory of the object, we can still define the work for any of the individual component forces that make up the net force. So even though these won't satisfy the differential equation that gives us this trajectory, they will have work associated with them. And that makes work a really interesting and useful quantity. Let me give you an example where this comes into play. So this is, again, a really 100 physics kind of example here. We're going to have a mass m sitting on the ground, and it'll be subject to a force external that's applied at a 45-degree angle to the ground. All right. Now, I'm going to say that this force is not large enough to lift the mass off the ground, so it's going to stay on the ground. And I want to figure out the work that's done as the mass moves a distance, let's say d, along the ground. Okay, let's begin with a free body diagram. We already have our F external. Let me go over that in pink. And then we'll also have a normal force from the ground and the force of gravity. If I sort of go through my forces in both directions, in the x direction, well, I have F external times the cosine of 45 degrees in the positive x, and that's it. So that's going to equal mx double dot. Fine. And then in the y direction, I have, well, what is it? I have Fn plus F external sine of 45 degrees minus Fg, which is mg in magnitude. And that's equal to my double dot. All right. Now, we don't actually need to solve Newton's laws. Merely, in this case, I want to say that because y is constrained to be 0, I know that this acceleration in the y direction is 0, which means that I happen to know what my normal force is in this case. It'll be mg minus this external force times the sine of 45 degrees. Which, by the way, is root 2 over 2. There's no reason to put it in at the moment. All right. The key thing to notice is that these two forces in the y direction that are purely in the y direction, the normal force and the force of gravity, don't cancel each other in this case. However, each of them can still be said to do 0 work on the mass. And why is that? The answer is because they are both applied purely in the y direction, and the object is only moving in the x direction. So when I compute the dot product of a force in the y direction with a path or the image of a curve only in the x direction, I'll definitely get 0. So the fact that these two forces don't balance doesn't matter. Neither of them does any work on the mass. And if I want to figure out the work done on the mass, I can look only at the work done by this external force. All right. So for instance, maybe I want to calculate what the velocity of this force, of this mass is at the end of the of its travel, at the end of this d distance. Well, I can use what I have stated here, but not as clearly as maybe I could have. So let's state a theorem, and then we'll apply it over here. I'm going to need a little bit of room here at the bottom, so let me make sure that I highlight this to show that it's important. This theorem is called the work kinetic energy theorem. And it merely says this, that this left-hand side is equal to the work along the curve. So the change in the kinetic energy along the path, which is again just the difference between the final kinetic energy and the initial kinetic energy, is equal to the work done on that path. And again, this is the total work. Now in this case, the total work is simple to compute for the reasons that we've specified. Additionally, let's say that the mass starts from rest. So we know that initially it has 0 kinetic energy. How much kinetic energy does it have at the end? Well, all I need to do is figure out what the work would be. The work, in this case, is going to be simple to compute, and that's because my line integral can just reduce to a regular dot product. So in this case, the work along my curve C is just equal to F external dot d in the x direction. And you can use the rules for line integrals to help you derive that this just turns into a regular dot product if you want. But we already know what fraction or what part of the force goes in the x direction. This is just F external magnitude times the cosine of 45 degrees, or if you like, it's F external root 2 over 2. Good. So now, what is the velocity at the end? Well, all I need to do is use the definition of kinetic energy. It's 1/2 times the mass times the velocity squared. So the velocity at the end must be related to the other quantities in the problem in the following way. We have 1/2 mvf squared is equal to f, oh, and I forgot my d here. So this should have been times d. So it's equal to F external times d root 2 over 2. Notice that these halves cancel. I move the m over to the other side, and I get that Vf is equal to the square root of F external d root 2 over m, sorry. All right, great. So there we go. The work kinetic energy theorem already allows us to determine something. It gives us the sense that this scalar quantity, the kinetic energy, has some relationship to the dynamics that is kind of nice. I want to draw that even further by starting to look at what we would call conservative forces. So I'm going to erase the board and we'll start there. All right, we have our work kinetic energy theorem up on the light board, and it's time to start looking at another scalar quantity that's going to help us connect back to this and prove the even more powerful theorem about conservation of energy that's really the focus of this part of the video. All right, so to do that, I'm actually going to need to back up and talk a little bit more about forces that we've been looking at in this course. Now, of course, when I've said that there's a force on a particle or on an object at a certain time, that does mean that at whatever time we're looking at, the force on an object is a vector that can be drawn on that object at that time. But oftentimes, it's really not clear that we know the force on an object at every time. Rather, we know the force given some other quantities that are true about the object. So for instance, its position or its velocity or the time independently. So I want to formalize that by defining what I'll call a force law. Okay, so by definition, a force law, curly F, is a function taking in, and maybe I should underline this, is a function taking in an object's position, velocity, and the time and outputting the force on the object. That is to say, the force on the object at time t is equal to the force law evaluated at time, so whatever time we're talking about, plus the object's, not plus, but and the object's position at that time, and the object's velocity at that time. Now, I'm sure that we could come up with an even more general definition of a force law, but all of the forces that we'll look at in this course are of this form. And I think you'll find that as you look through the possible forces that you can think of in nature, most of them fit this model. Great. Okay, let's jump directly to a special case. That's the special case where this force law does not depend on the velocity. That turns out to be an especially nice situation. So, another definition, a force field is a force law that does not depend on the velocity. So what would make that nice? Well, the answer is that if this doesn't depend on the velocity, then we can think of this curly f object as being a function, a time-dependent function, from Rn to Rn. And an object that's a function from Rn to Rn is our definition of a vector field. Okay, so let's point out a force field defines a vector field at each time. Curly f of t. Great. And we have a lot of theorems that let us deal with vector fields. Now, I'm making a supplementary video that is going to go through a lot of the vector calculus theorems that you might have seen in one form or another, and hopes to relate all of these different ways together and at least just go through them. So I'm going to go pretty fast through vector calculus propositions and theorems in this video today. The first one, which you may or may not have seen so far, but which is absolutely essential all over the place in physics, is the so-called Helmholtz theorem. So let me go ahead and get that on the board. So we'll need the Helmholtz theorem here. And that says the following. If V is a vector field, so let me say if V is a vector field, then V can be decomposed in the following way. V is equal to minus the gradient of phi plus another component that I'll call Q. Okay, where Q satisfies del dot Q is equal to 0. So just a recap or a refresher, del, this object, acting on a function, so phi is a function, is called the gradient. The gradient is an object which takes a function to a vector field. Okay? This object down here is the divergence. The divergence is an object which takes a vector field like Q to a function. And in this case, it takes it to the 0 function. Great. Okay, so in 3 dimensions, we have a special case of the Helmholtz theorem. So in 3D, we can say V is equal to minus del phi plus del cross C for some vector field. where del cross is the curl. The curl is another object which takes a vector field in, but in this case, it produces another vector field. So this object is still a vector field. Wonderful. Now, a few things about the Helmholtz decomposition. One thing I haven't said is that these functions are unique. The Helmholtz theorem says that there exists a function that does this. So maybe I should say that explicitly. So maybe I should say there exist phi and q such that that is true. But it doesn't say that we could find them uniquely. The second thing is that we have to be a little bit careful, which we often aren't as physicists, about what kind of space we're talking about. Are we talking about all of Rn? Are we talking about some subset of Rn? What are the properties of that subset? And I will let you go and look up the hypotheses. Basically, if you want to think about it from a formal mathematical perspective, this works most nicely when one of a few of the following is true. Either V could be only non-zero on some subset of Rn, or we can do it when V dies off quickly enough as we go out to infinity in Rn. Or it turns out we can even do it if V is everywhere a polynomial function on Rn. So there are a number of different settings where we can state this in the most formal way possible. But for our purposes, we're okay with just assuming it. Okay. Now, I want to keep this in mind and jump to something that seems completely unrelated. So I'm going to do another definition. You'll notice the board is just filling up with definitions at this point. So if you need to pause and go back at any point, that's all right with me. Okay, so another definition. A conservative force field is one such that two things are true. One, F does not depend on T. Good. So it's the same vector field through all time. And two, F, I should say, the work done by F on a path from, let's say, A to B. Let me draw a little figure here. So A is going to be some point in Rn, and so is B. Does not depend on the path, only the endpoints. All right, wonderful. So a conservative force field is one such that, again, the vector field is the same for all of time. Also, if we take this path, the work that's done on the object is the same as if we took this path. All right. Now remember that because the work can be calculated or can be computed for any force which forms a component of the net force, it doesn't need to be the case that we look at the actual trajectory that the object would follow under only the force F. We can look at any given trajectory. And that means I'm allowed to look at the work done only by this force field F over both of these two trajectories. And if the work is the same in both cases, then I'm all good. I have a conservative force field. Now comes where we need some bigger machinery. And actually what I'm going to do is start by just seemingly out of nowhere looking at this thing, this Helmholtz equation, and using it, applying it for my force field. So Helmholtz theorem says that for a force, so let's say for a force field satisfying 1. So in other words, it's time independent. We have the following. F is equal to, well, let's just use this notation. I'm going to change here my phi to a u, just to say that I'm working specifically for force fields. Okay, and then plus del cross C, just as I have over there. Now I'm going to look at what the work done by F is along some path. Okay, so I want to look at work done along a path curly C, which again is going to be now F dot dr, or equivalently, well, actually, let me go to another line. I'm going to use my Helmholtz theorem here. So I'm going to say that this is equal to, oops, the integral over C of minus, so I'll pull the minus out, del u dot dr plus the integral over C of del cross C dot dr. Great. Okay, now the only property that I use to get to this line is the fact that the integral is a linear operator. So if I have the integral of the sum of two functions, that's the same as the sum of the integrals. And that holds true as well when we have vector integrals, or I should say line integrals like we do here. Good. Okay, to apply my big theorems, I actually need to choose one more piece of data about all of this. Now, I've assumed up till now that I'm looking at a curve C that goes from like A to B. But if I have two such curves, let's call this one C, and we'll call this pink one C prime, I'm allowed to think of a new curve, C double prime, which is going around C and then backwards around C prime. So I can think of this, the curve that goes this way first and then this way, and I'll call that C double prime. So I'll say C double prime is C and then C invert or C prime backwards. So I'll maybe denote it like that. Okay, so I actually want to do all of this not along C, my original C, but along C double prime, because C double prime has a really important property. C double prime is a closed loop. Okay, so note C double prime is a closed loop. And that's super important for what we're going to do now. All right, now let's bust out the big machinery. The first theorem that we're going to need is the so-called gradient theorem. Which is really just a generalization of the fundamental theorem of calculus. And it says the following. If I take the integral along C of the gradient of a function f dot dr, that is just equal to the difference in f between the endpoints. So I'll say f of b minus f of a. Great. And you'll see exactly how similar it is to the fundamental theorem of calculus. Now, what we'll need for this last case is what's called Stokes's theorem. You may have already encountered Stokes's theorem if you've studied E&M, where we use it to figure out how to use Ampere's law to find the magnetic field. Okay, now what Stokes's theorem says is that if I take the integral over a region, a two-dimensional region R, of the curl of some vector field dot dA. So now this is a surface integral over a two-dimensional region R. That is equal to the integral over the boundary of R, which in math is often denoted using the partial symbol. So partial R means the boundary of R, of V dot dr. Okay. So our goal here is going to be to use Stokes's theorem in reverse, we've set up C double prime so that it is the boundary of something. Namely, the region R for us is this region here in the center. So we can relate this back. Okay, let's use these two theorems to really super reduce this expression. So we get that the work done over C double prime is exactly equal to what we get from the first term by the gradient theorem. But notice that that tells us that we should get f of b minus f of a. For C double prime, both the beginning and the endpoint are a. So we'll get 0 from this first part. Maybe actually let me go over that in pink just to show that that's where it comes from. And then from this second part, using Stokes' theorem, again in reverse, we get plus the integral over r of the curl of of C dot dA. Okay, now I could work relatively hard and show you that this integral is non-zero in general, but I don't even really have to do that. And that's because if I want to think about the possibility of this curly f being a conservative vector field, I need it to be the case that the work done by curly f on a path from A to B does not depend on the path at all. So this needs to be true not merely for a given C double prime, but for every C double prime. And it seems really unlikely, and in fact it is not true, that I can make this last integral true for any region R that I could come up with. So we can we find the following: a vector field is conservative if and only if. So let me just squeeze this in up here. F is equal to minus nabla u. That motivates us to define this object on the right-hand side. We call this object the potential energy. I should say just u is called the potential energy. All right. So potential energy is an object that you have certainly seen if you've completed an introductory physics course, but it came up in a somewhat different way here. In our case, we said that we were interested in trying to use scalar quantities rather than vector quantities as much as possible in describing dynamics, because scalar quantities are much easier to work with in many ways. We defined the kinetic energy and found the work kinetic energy theorem. That was a big deal because it told us that this kinetic energy, this thing that seems to characterize the motion, depended in a nice way on some line integral of the force. Now, we've tried to connect that, along some long chain of reasoning to some other scalar quantity, the potential energy. And the potential energy came in because it makes, if we have a force field, or a force field that only depends on a potential energy, then we're in a good position to describe that line integral simply. All right, so let's do that, and we'll do that just down here. I think we can squeeze it in. So I'm going to note that this tells us, so if C is equal to 0, so if we have no curl term, then the work on C is something that we can get. It is just equal to U at the endpoint B. Remember that the endpoints of C really are A and B, minus U, minus U of A. Great. Now, let's take this together with the work kinetic energy theorem, and we'll finally get what we've been promising all along. So, if we end up in the case where we have a conservative force field, then we get the following. So, for a conservative force field, I'll say t of b, but really this needs to be interpreted as t at the time that we reach b. Hopefully it's clear. Minus t of a. And I'm realizing that I made a little sign error down here. Notice that this has a minus sign here. So this is actually minus ub plus ua. Sorry about that. All right. That's important because I'm now going to connect these two since they're both equal to w of c. So this is equal to minus u of b plus u of a. And with just a little more rearrangement, we find that t of a plus u of a is equal to t of b plus u of b. In other words, the sum of these two objects is a constant everywhere along the curve C. And this applies for any curve C. Evidently, this object represents a conservation law. So this represents conservation of mechanical energy. Where the mechanical energy is, by definition, the sum of the kinetic energy and the potential energy. Okay, so before we go on and do some examples on the computer, I want to summarize what we've done. While we haven't shown yet that we can get the dynamics from this kind of, from this kind of approach, we have shown the following. That if we only have an object subject to conservative force fields, or if only conservative force fields do work on an object, such that any non-conservative forces in our problem aren't doing any work, then mechanical energy is conserved all the time. So if we look at the space of different trajectories our object could take, we know that any that don't conserve mechanical energy are impossible. That seems to maybe limit the space of possible trajectories for our object, but it doesn't limit it down to one. The big promise of Newton's second law was that it allowed us to answer, again, Halley's second question. Again, given known forces, can we calculate the trajectory? In this case, we saw that for known for a known conservative force field, we can get something, we can limit the space of possible trajectories, but we don't get exactly to one trajectory most of the time. However, as it turns out, if we have motion for only one variable, we can actually get the trajectory. And that's basically because we now only have one equation and one unknown. Notice that the statement that the mechanical energy at any later time in the problem is equal to some initial value, the initial mechanical energy, represents a differential equation precisely because t involves derivatives of the trajectory and u depends on where you are in position space. So these are both functions that depend on the trajectory of the object. Meanwhile, one side of the equation can be considered a constant. It's the known initial mechanical energy of the system. So in that case, we are actually able to solve. So let's hop to the computer and we'll look at a bunch of examples where we can use the fact that we are in a situation where the system is described by only one variable to actually solve for the trajectory given a known conservative force field. I'll see you over there. All right, let's work out a few examples that show us how to use energy for systems that can be parameterized by a single variable. The simplest example is a system that is simply one-dimensional, by design. So, for instance, we could consider a mass on a spring, very typical example, that can only move in one dimension, say the x direction. All right, well, we know how to do this with forces, but let's do it with energy. We'll see that in this case, we can use energy to solve for the trajectory given a known potential energy function. All right. In this case, the potential energy function, this is probably something you know from introductory physics, is 1/2 kx squared. We'll just say that the spring, maybe I shouldn't put a wall here, the spring is, fixed at the origin and has equilibrium length 0. Let's bring that back. Oops, there we go. Okay, now what this means is that the total mechanical energy, E, is going to be given by 1/2 kx squared plus 1/2 m x dot squared. Good. Now, we also know that this is going to be equal to the initial total mechanical energy. The other initial condition we need is the initial position. So I'll say we also have initial position x naught. Good. Now I have a diffie-q that I can solve. This is one diffie-q with one extra initial condition. So let's rearrange it so that we're solving for x dot. Okay, the first thing that I would need to do is move 1/2 kx squared to the other side. Then I could multiply by 2, divide by k. So let me do all of that stuff. 2e naught minus mx dot squared, all of that over k. Then I would need to take a square root. Good. All right. So this is my ODE for x. Oh, and that shouldn't be an x dot. That should be an x. And this shouldn't be a k. That should be a k, and this should be an m. Error there. Anyway, ODE for x with initial condition x of 0 is equal to x naught. Remember that a first order ODE only needs a single initial condition. Now this is an autonomous first order ODE, which means it's separable. Say that implies separable. So the way that we generally approach equations like this is to imagine that this, on this side we have dx dt, we'll move the dt to the other side and then we'll integrate both sides. So on the left-hand side, we'll get all the x terms. We'll collect all the x terms there. So maybe let me write this in an integral sign because we want to take the antiderivative. We're going to take the antiderivative of the inverse of this thing. So square root of m over 2e naught minus kx squared dx, and that is going to be equal to the antiderivative, I should say, of dt plus a constant. We'll put the constant on that side. Let's just carry out the right-hand side right away. That's going to be t plus a constant. Good. Okay, the left-hand side is actually going to require some work. What we're going to need to do is a u substitution. The u substitution that we need to do will make this term, this whole term, into something that looks like 2e naught times, let's say, sine squared of theta for some theta. So what is the u substitution? In this case, a theta substitution that will do that. Well, if I divide it over, it looks like I'm going to need x is equal to root 2e naught over k sine of theta. Okay.
that means that dx, which I have out here, is going to equal root 2 e naught over k times, well, I'll need to take cosine theta d theta. All right, and I don't need to worry about bounds because I'm just trying to calculate an antiderivative. All right, so after I do that substitution, I'm going to get root m over 2e naught minus 2e naught times sine squared theta, that was by construction, times root 2 e naught over k cos theta d theta is equal to t plus c. Good. Now I need to use my Pythagorean identity to do something with this. This denominator here is equal to 2e times 1 minus sine squared theta, but that's, 2e naught, but that's equal to 2e naught times cos squared theta. Oops. All right. So let's look at that. If we pull the cosine squared out of the square root sign, we can do that as long as we turn cosine squared theta into cosine of theta. In this case, that is no problem. We'll just be dealing with a region where theta is such that it can come out without having to use absolute value signs. So what will we get in the end? Well, I can already separate out an m over 2e naught. Then I have just 1 over cosine squared theta left over. 1 over cosine squared theta left over. So I'll just get a 1 over cos theta. But then I also have a cos theta from here. So let me make sure I don't forget my 2e naught over k. Cos theta d theta is equal to t plus c. Should be noting that all of these are implications. All right, we get some cancellations. This 2e cancels with that 2e, I should say root 2e. This cos theta cancels with that cos theta. And all in all, we get root m over k times integral d theta is equal to t plus c. But integral d theta is just theta. So that's root m over k theta is equal to t plus c. Now we need to replace theta by exactly its definition here. So if x is equal to this factor times sine theta, that implies that sine theta is equal to root k over 2e naught times x, which implies that theta is equal to the inverse sine, the arc sine, of root k over 2e naught x. Good. Okay, so down here, we now have root m over k sine inverse of root k over 2e naught x is equal to t plus c. Now we use our initial condition. The initial condition will tell us what c has to be, this constant here. And without too much difficulty, if I use the initial condition, I'll be setting this t to 0 and this x to x naught. So that will imply that c is equal to root m over k sine inverse of square root k over 2e naught x naught. Good. Now I'd like to solve for x, so I need to start moving things around. Okay, first let me multiply over to the other side my root k over m. Okay, so I get k over 2e naught x is equal to root k over m times, well, times t. Then I need to say plus c, but notice that the root k over m is just going to cancel this factor. So we'll say plus sine inverse of square root k over 2e naught x naught. Good. And I'm actually going to make a correction way back up at the top, or just a clarification. Typically, when I say the square root, I always mean the positive square root of a real number. So I should really have put a plus or minus sign here. That means I should have a plus or minus sign all the way down. Including in C, because now my initial condition will just match the sign. All right. What that ends up doing here is meaning that when I multiply over this constant, I'll multiply a plus or minus over with it. So I get this. Great. Okay, so now I'm almost done. I can say x is equal to, after moving everything around, 2e naught over k times the sine of plus or minus root k over mt plus arc sine of root k over 2e naught x naught. Now this doesn't look exactly like what you're familiar with from doing a section on oscillations in perhaps a 100 or 200 level course, but it is. This is an oscillation in the form a sine omega t plus delta, or maybe sometimes it's minus delta. Notice that this root k over m is exactly the angular frequency we expect for a spring in this configuration. Okay, so I could go through and show that this is the correct amplitude and that this is the, well, I should say this is definitely correct, but that this is the correct phase shift. But it's okay, we don't have to go all the way with this. I merely want to show that we do get the correct result using energy. All right, now let's do a slightly more surprising application. It's not that surprising that because energy sort of preserved some features of the motion in 1D, that we could take a 1D problem and use energy to solve it. What is surprising is that there are systems which aren't truly one-dimensional, but which behave like one-dimensional systems. So the times that this can happen are somewhat varied. The first we saw earlier on when we considered the following situation. Imagine that I have a mass which is being pulled by an external force in this direction, but such that it's not a strong enough force to lift the mass. Now what I'm going to get is that gravity is slightly stronger than my normal force. So these two don't balance. So even though my forces in the y direction from the normal force and from gravity aren't balanced, it's okay. The net work that's being done is only being done by this force, but only its x component is doing work. So that's one case where the motion ends up being one-dimensional, even though the forces are not all in 1D. So forces of constraint can sometimes be perpendicular to the motion, even if motion is 1D. But in this case, we are kind of still dealing with a 1D problem because the force of constraint is simply adjusting itself based on the other forces. And that's always going to leave the motion one-dimensional. A more interesting example is the example of Atwood machines. Okay, so let's draw a good Atwood machine. Maybe these should be a little bit closer. I'm actually going to start with my pulley. So an Atwood machine involves a string, which is draped over a pulley. And on the two ends are connected two masses. Here we have M1 and M2. Okay, good. Now, in an ideal Atwood machine, we'll say the pulley is massless, And we'll say that there's no mechanical energy loss in the system. Okay. Now we could solve this using forces. Let's do it really quickly. So we have the force of tension on the first one. We have the force down of gravity on the first one, m1g. We have the force of tension on the second one, and the force of gravity on the second one. Now our rules for strings tell us that when we have two ends of a string that are draped over a massless pulley, then the tension on the two is equal. So this is equal to this. Ft sub 1 in magnitude is equal to Ft sub 2. In this case, also in direction, but an Atwood machine could be created such that the string was not in the same direction, and the tension statement would still be the same for the magnitudes. Okay, anyway, so here we'll do it with Newton's second law. For each mass, we need to look at both, we need to only look at the y direction because the motion is constrained to be in the y direction. Okay. For mass 1, we get the following. m1 times y1 double dot is equal to, well, what are the forces? F sub t, let me just call it F sub t for both of them. Okay, minus m1g. Similarly, m2 y2 double dot is equal to ft minus m2g. Now we can say that the total length of the string is L. Excluding the part over the pulley. All right. That means that y1, if y1 is this distance, or is this coordinate, then y1 plus y2, which is this coordinate, well, that's equal to L. I guess it depends on where we measure it from. So for instance, if we say y is the distance above this, which maybe we should, then actually these are at positions y1 and y2, which are negative, and we would actually have the following. So maybe just for consistency, I'll say that. So y1 is the distance above this center line. But either way we do it, we'll get the following when we take the second derivative. We get that y1 double dot plus y2 double dot is equal to 0. Or equivalently, we get that y1 double dot is equal to minus y2 double dot. Okay, so what we can do is rewrite this second equation in terms of y1 double dot. So we get minus m2 y1 double dot is equal to ft minus m2g. Now we're going to just subtract these equations from each other. m1 y1 double dot is equal to ft minus m1g. So as I said, I'm going to subtract these. That's going to eliminate my force of tension. All right, so I'm going to get m1 plus m2, that's from this minus and this minus, times y1 double dot is equal to, well, the forces of tension cancel, and instead I'm just going to get minus m1g plus m2g, which implies y1 double dot is equal to m2 minus m1g over m1 plus m2. So this is kind of the principle of an Atwood machine. It experiences a constant acceleration, so y1 double dot is the acceleration. This is the magnitude of that constant acceleration, but the acceleration isn't just g, it's g multiplied by some complicated factor of the two masses. All right. So we know we can do this in terms of forces, at least get to this ODE. can we do it in terms of energy? Well, it seems like we shouldn't be able to, because in addition to the conservative forces of gravity on the two masses, we have this non-conservative force of tension. So how do we deal with the non-conservative force of tension? To see how, let's imagine that this system evolves in time. Here's time 1, and it evolves here, so M1 and M2, and we're going to say that M1 goes up. That's going to mean that M2 goes down. Okay, so let's say that M1 went up by a height h. Okay. Now, think about what the forces of tension are as this is happening. The force of tension on M1 looks like this, and the force of tension on M2 looks exactly the same force vector. But the displacements look different. The displacement on this one is this, it's h times, let's say, y hat. But the displacement on this one has to be minus h y hat. So overall, the work done on the system of the two masses is, so let me just say work in general, in total, is Ft dot, this first one, h y hat, so this is from M1, minus Ft dot h y hat. And this is from mass 2. But that's definitely equal to 0. So, in this case, the constraint force does no work on the system as a whole. It does work on the individual masses, but it does not do work on the system. And that is going to happen in lots of cases where you have forces of constraint that do act in the same direction as the motion. Okay, what this means is that the constraint force does not need to be considered as we work in energy. So we can set up an energy equation that says that the mechanical energy, where we only consider the potential energy from the conservative forces of gravity and the kinetic energy, we'll say that that thing is conserved. Okay, so now the energy of the system as a whole is equal to 1/2 m times, well, what should we use as our one constraint? Let's first write it in terms of y1 dot squared, and that should have been m1, m2, y2 dot squared. Then we'll need to use, okay, so I guess we're now saying that y is the distance above this line. So we'll say plus m1 gy1 plus m2 gy2. Great. The key is that we can use this equation to solve for y2 in terms of y1. This equation implies that y2, if I move it to the other side here, is equal to minus y1 minus L. Good. Okay. So that's what I'm going to do. I'm going to use y2 is equal to minus y1 minus L to say a couple of things. The first is that y2 dot is equal to, well, just minus y1 dot. And the second is that I can just plug all of that into this equation and rewrite it in terms of a single variable. And that's how I get back to an energy that depends just on a single variable. Okay, so I have 1/2 m1 y1 dot squared plus 1/2 m2 times times y1 dot squared. Notice that doesn't depend on the sign, so it doesn't matter that this has a minus sign here. plus m1 gy1 plus m2g times minus y1 minus L. All right, now I'm going to exploit an important feature of mechanical energy, which is that if there's a portion of the mechanical energy, a term which is constant over the entire trajectory, then that term just doesn't have any effect at all. I'm allowed to ignore it. This term here, that depends on L, I can ignore because it's constant. Every position has that part of the energy, so it doesn't have any dynamical effect at all. So now, if I rewrite that with my ignoring that one constant, so this is equal if I ignore that term, then I get 1/2, now m1 plus m2, y, instead of saying y1, let's also set y1 to y, just so that we don't have to keep writing it. So I get 1/2 m1 plus m2 y squared plus m1 minus m2 gy. Good. And sorry, that should have been y1, y dot squared. Okay, just like before, we say that that's equal to the initial energy, and we're going to need some initial position. Now, once again, we have an initial value problem that we could solve. In this case, the solution is, in some senses, a little bit easier. All right, let's first, before we do it, it turns out in this case that we actually get a much nicer equation to solve by non-dimensionalizing. So let's first get our ODE such that y dot is by itself, and then we'll non-dimensionalize. Okay, here we're going to first get y dot squared is equal to, well, if I multiply over to the other side, a 2 and then divide by m1 plus m2, I'll get 2e naught over m1 plus m2, and then minus m1 minus m2 gy over m1 plus m2, and I do also need to multiply by 2. Good. Now I can get rid of that square if I take the square root. Now I'm going to actually elide the fact that I need to take either the plus or minus sign here for the time being. That turns out not to matter, and you can work out the details for yourself, but it makes it a little bit messy. You'll get solutions that work if you just consider this one. So let's do that. All right, now my non-dimensionalization. Actually, let me cut that. I'm going to go back. And just as before, I need to include my plus minus here. All right, now I'm ready to non-dimensionalize. And my constants are, well, I have 2e naught over m1 plus m2. I have 2 times, I'm going to write it as absolute value m1 minus m2, g over m1 plus m2. Now that's because I want my constants to always be positive. And so if I use this absolute value here, that's what I'll get. And then lastly, I have y naught. That's also a constant. Now it's not super obvious which ones I should want to pick to do a good non-dimensionalization. And I think the answer is actually just not obvious. You could pick any two of them, it turns out. But I'm going to pick this and this. That means that my reference length is y naught, because that already has units of length. And if we think about this object, well, I know that energy, one kind of energy is kinetic energy, and it can be written 1/2 mv squared. So if I take an energy and I divide by mass, I have something that has dimensions of velocity squared. So this thing has dimensions of velocity squared. All right, that means if I take the square root of this thing, I have something with dimensions of velocity. And if I divide a length by a velocity, then I get a time. So that tells me that T ref should be equal to y naught divided by the square root of this thing, or multiplied by m1 plus m2 over 2e naught. Great. Okay, let's let y over L ref equal xc and t over t ref equal tau. Good. Now my equation can be rewritten. I'll have my reference velocity, which I know is root 2 e naught over m1 plus m2 times c prime, that replaces this left-hand side, is equal to plus or minus the square root of 2 e naught over m1 plus m2 minus 2m1 minus m2 g y naught c over m1 plus m2. Okay, now I'm going to multiply by the inverse of this thing to get c prime is equal to plus or minus. Well, for the first one, it just is going to turn into a 1 for the first factor, I should say. For the second factor, I'm going to have, well, the 2's will cancel, the m1 plus m2 will cancel, and I'll get m1 minus m2 g y naught over e naught. Good. And then times c. So now I need to write this in terms of a dimensionless parameter. This thing is dimensionless, but I'm not going to write this by itself as a single dimensionless parameter, and that's because it's not always positive. It depends on the sign of m1 minus m2. So I'm going to write it in the following way. I'll say plus or minus the square root of 1 minus s alpha c, where s is equal to the sine function, signum function sometimes, of m1 minus m2, which is plus 1 if m1 is greater than m2, and is minus 1, oops, I should say plus 1, minus 1 if m1 is less than m2, such that this can tell me whether or not m1 minus m2 is positive or negative. Then alpha is going to be equal to, well, it'll be my m1 minus m2 absolute value, gy naught over e naught. Great. Okay, now I have a diffie-q that I can solve, and it's the same kind. It's an autonomous first-order equation, so it's separable. All right, I'm going to get a very similar kind of structure to what I had in the last case. So I get over 1 minus s alpha c, oops, is equal to integral tau, d tau plus c, which is equal to tau plus c. Good. Once again, I need to make a u substitution, and the u substitution is just going to be all this stuff is equal to u. So u is equal to 1 minus s alpha c. That implies that, well, first of all, du is equal to minus s alpha dc. Oh, and that says dc prime, it should just say dc. So that this whole integral becomes the integral of 1 over minus s alpha integral du over u to the 1/2. Now that in turn, to get u to the 1/2, I would need to have, or sorry, u to the minus 1/2, because this is in the denominator, I would need something that's proportional to u to the 1/2. But then I need a 2 on the outside. So this is going to give me minus 2 over s alpha square root of let me say u to the 1/2 upstairs. Good. Which is, of course, equal to minus 2 over s alpha square root of 1 minus s alpha. Good. All right. So next up, let me write out what I have so far. Minus 2 over S alpha, root 1 minus S alpha. Oh, and I have screwed this up in one big way. I forgot to include the xi here. So this should have been xi. Is equal to tau plus c. All right, we now need to use the initial condition. Minus 2 over S alpha, 1 minus S alpha. So xi of 0 is what? Well, it's equal to y of 0 over y naught, but y of 0 is y naught, so it's equal to 1. Good. That is equal to 0 plus c, so that's what c is. All right, so now we're almost home free. We have minus 2 over S alpha. And I have made one more mistake. I dropped my plus minus that was here. So in the end, this actually becomes a minus plus. Good. This also becomes a minus plus. All right. Minus plus 1 minus S alpha xi is equal to tau minus plus 2 over S alpha, root 1 minus S alpha. Okay, let's multiply through by this factor. 1 minus S alpha xi square root is equal to minus plus S alpha tau over 2, and then plus root 1 minus S alpha. Now we need to square this, because the square root is here. 1 minus S alpha xi is equal to, okay, so when I'm squaring, I'm going to need to square a binomial. That means I need to deal with all the terms. So first I'm going to get the square of this thing, which is S squared, alpha squared, tau squared over 4. Next, I get 2 times the product. Now that 2 is going to cancel the 2 in the denominator here, so I'll just get S alpha tau root 1 minus S alpha. And lastly, I am going to get this thing squared, so plus 1 minus S alpha. Okay, there's one simplification that I can make here, which is that S squared, S is either plus or minus 1, so S squared is always 1. Good. Sorry, I should say there's another simplification too, which is that I have a 1 on both sides, so I can just cancel that out. All right, the last thing is I can multiply through by 1 over S alpha. So let's actually do that in a new line. So I'll get xi, I guess I'll also include this minus sign. So xi is equal to minus alpha squared tau squared over 4 alpha s, okay, plus S alpha over S alpha, oh, and it should be minus because of that sign, minus this, tau 1 minus S alpha, good. And then lastly, I have a minus S alpha here, so that's gonna just cancel and I'll just get plus 1. This also obviously cancels, so I just get that. Good. And I guess while I'm making cancellations, this 4 alpha s should just become alpha over 4s. And then s is the same in the numerator or denominator, so I might as well move it to the numerator. All right. Now this is looking pretty good. And in fact, just like in the last one, I'm not super concerned with taking it all the way home. Rather, let's remember what we got in the case where we did this with Newton's second law. We got that this should be just constant acceleration motion. And constant acceleration, you know from kinematics, will always give you something like y1 is equal to 1/2 at squared plus vt plus c. Down here, that is exactly what we have. Notice that we have a term proportional to tau squared, a term proportional to tau, and a term that is 1 in the non-dimensionalized units. So we get back the correct constant acceleration type motion. All right. Now, I want to point out something really important about everything we've done so far while working out these examples. It's true that we can do things this way because we can turn something into a one parameter, one variable function. But it's not clear that we've gained anything in either of these cases by using energy rather than Newton's second law. And that's because I picked very simple examples where there's really not much to be gained over Newton's second law. The differential equations we obtain from Newton's second law are simply very simple to solve relative to other differential equations that we might try to solve. So in this case, we didn't really gain anything by using this new method. It was expanding our horizons of what we knew how to do, but it wasn't necessarily actually better than what we already knew. But there is another way that this kind of thinking about problems can be really helpful, and that is in thinking about equilibrium. Okay, so we actually need to introduce a definition. So that example's done. Definition. An equilibrium point of a function, or sorry, of a system subject only to conservative forces or other forces that do no work is a point or a position, let me say, such that the object is subject to no force. A stable equilibrium point is one such that slightly displacing the object causes it to oscillate around the equilibrium point. Let's underline all of that. Good. Okay. Now the key is that even if u is a function of some parameter, let's say b, where b is not the actual position. So for instance, when we dealt with the Atwood machine, the position y of one of the masses served as a sort of parameter for the entire system. As long as there's only one parameter b that describes the entire system, then I can state equilibrium in terms of information about this function. So I'll say this is potential energy of the system at parameter b. Okay. So now we can state, a statement. So I'll just say fact that is both true and very useful. Equilibrium point, I should say an equilibrium point, is one such that u prime of b is equal to 0, and a stable equilibrium point is one such that u double prime of at b is greater than 0. So let's draw our plot of u. Here's u as a function of b, and whatever, something like that. Now, equilibrium points are all of the points in red, all the places where the first derivative is 0, sorry. Where are the equilibrium points? Let me see, like that. The stable equilibrium points are the places where it looks like an upward facing parabola, in other words, where it's concave up. So this is a stable equilibrium point, that is, and this is. Okay, let's deal with one more example, and then we'll get back to the light board. Okay, so we're going to have a cylinder which is fixed, on the ground. And a cubic object on top of it. Let's say it has side length L. That's balanced, and this can have radius R. Good. Let's give this mass M. Now, friction is such that this cube can just roll back and forth on the cylinder. So let me point out the cylinder is fixed, so it doesn't roll. I guess I'm doing this the opposite way. Cube can roll. Okay, now, if the cube rolls, then it could get to another position. Perhaps it is here. We could describe it, for instance, by the angle with which it's rolled, right? And I shouldn't draw it as being centered here because now it will be actually off center. Okay. Now, what happens while this rolling is happening? Well, the answer is that the position, the distance, I should say, from the center to this point, so this is going to be the center line. Let me say this is the center line. So this distance here is equal to the distance that it has actually rolled. So if this distance is s, then this distance is also s. Good. Now this is one of the cases in which we can use the center of mass to tell us what the potential energy of the object is. So here, U is equal to just mgh, where h is the height of the center of mass. Great. Okay, now there's going to be some triangle drawing to do, because I know how to get to the center of mass in this case. Oops. All right, so this length is r. This angle, remember, is theta. What I need to do to get to the center of mass, I know that I need to go up a distance L over 2. And then I need to go across a distance S. That's S. All right. Good. So the question is, how different is that from the original position of the center of mass, which again was just a distance L over 2 up here. Original center of mass. Okay, so let's just denote the location of the center of mass. So the original, again, we only care about the height. The original height was r plus L over 2. What about the new height? Well, we're going to need to do some trig to figure that out. The height of this point here, I can figure out relatively easily because this angle is theta. So this length here, well, that is the side adjacent to theta. So this is going to be r plus L over 2 times the cosine of theta. But that isn't actually the height of the center of mass. For that, I need to keep going. Okay, that angle is theta. And that means if I draw a horizontal line here, well, this angle must also be theta. And why is that? This angle is 90 degrees, and this angle is also 90 degrees. So that gives me that this is theta. So the height that I need to add, well, now I need to go s length, but I'm adding the opposite side. So this length here is s times sine of theta. Now, what is the length s? Well, that is exactly the distance that of this arc here. But if I'm measuring theta in radians, then that distance is r theta. S is equal to r theta. So some relatively involved trig, but nothing more than that here. Okay, so what do I get? I get r plus L over 2 cos theta plus r theta times sine theta. Good. Now, it's always good to sort of check ourselves in terms of like a sense check. So let's quickly do that by thinking about what happens when theta equals 0. Does this go to the right thing? And indeed it does. Notice that if theta goes to 0, that's going to go to 1. Takes this back to r plus L over 2. And this goes to 0. So we're good. All right. So I can say that the height is the height below this thing. So the height measured from original height. In other words, this line is going to be where height equals 0, if I could draw a straight line. So we'll get a negative. All right. Okay, so here's the potential energy we're going to work from. Now, let's go ahead and take our derivatives so that we can find equilibrium points and see if they're stable. Okay, we'll start with u prime of theta. So, of course, if I take a theta derivative of this, it goes through everything except the trig functions and then this theta here. On the first term, we'll just have r plus L over 2 times minus sine of theta. Then on the second term, we'll have to use the product rule. So first we'll have r sine theta, taking a derivative of this theta. Then we'll have an r theta cos theta, taking a derivative of this sine of theta. Something kind of interesting happens here. Notice that this r, this gives us a minus r sine theta, which cancels with that plus r sine theta there. If we want to solve for equilibrium points, then we want to set this equal to 0. So let's rewrite that equation. Notice mg doesn't matter here, so we can drop it at this stage. This gives us L over 2 times minus sine theta plus r theta cos theta is equal to 0. Or equivalently, moving things around a little bit, we get, let's see. Well, first we get L over 2 sine theta is equal to r theta cos theta. Let's divide the cos theta over to the other side and then multiply the 2 over L over to the other side. So all in all, we'll get tan theta is equal to 2r over L times theta. Now this kind of equation is called a transcendental equation. It's typically what you get when you have an equation that relates a trig function to a polynomial. So that's what we have here, a trig function on this side, a polynomial on this side. And that means that the equation does not have a closed form solution. But we can look at it using plotting software. So I'll use Mathematica in this case. Okay. Let's pull open a Mathematica notebook. And a little error here. Here we go. So here we go. I have already written this code. There's a manipulate function that allows us to tune the variable alpha, which is our 2r over L. Okay, so what we have here is the blue curve is alpha theta, and the yellow curve is tan theta. There's definitely a solution at theta equals 0, and then there's also another solution. But there's only a second solution some of the time. There's a solution exactly when, well, let's look, see if we can zoom in and figure it out. If I blow this up, it should be easier to see. Okay, so I can see alpha down here, a little bit small, but right now it's about 0.485. And it looks like I get another solution exactly when alpha equals 1. And that's true. I'm not going to prove it because it's a relatively simple exercise in calculus. But what you can do is show that both of these functions are increasing. So both alpha theta and tan theta are increasing. But tan theta will have a slope which is always greater than alpha theta if alpha is less than 1, which means that they will never intersect. However, if alpha is greater than 1, then the fact that that tan theta eventually has a higher slope and overtakes it means that you must have some intersection. Okay, so in this case, alpha greater than 1, we do get an intersection. So let's go ahead and write that down. So solutions, we have, theta is equal to 0 always. And we have theta alpha greater than 1, not alpha, 2r over L greater than 1. We have a second solution somewhere. I'll say for theta greater than 0. And we're only going to look at, again, between 0 and pi over 2. Of course, there's another solution on the other side for theta negative. Okay, let's evaluate the stability of these solutions by looking at u double prime of theta. That's relatively easy because we already have u prime of theta if we just ignore the equals 0. And we'll have to keep the mg around. Okay, so u double prime of theta is equal to mg times, well, first I have L over 2 minus sine theta. Taking the derivative of minus sine theta, I'm going to get minus cos theta. So minus L over 2 cos theta is my first term. Next, I have this term, and once again, I need to use the product rule. So I have plus r cos theta, and then minus, if I take the derivative of this second term, r theta sine theta. Good. Or if I regroup my terms, I get mg times r minus L over 2 cos theta minus r theta sine theta. Good. All right. So let's see, when is this greater than 0? So let me write in greater than 0, and we'll just see when this condition is true. Once again, I can divide by a positive, so I can divide by mg. So let me say this is when r minus L over 2 cos theta is greater than r theta sine theta. Okay, great. Next, I can divide by cos theta. And why can I divide by cos theta? Well, assuming that theta isn't 0. So actually, maybe we should right away check theta 0. And theta equals pi over 2. But theta equals pi over 2 isn't even an equilibrium point, so we don't need to check it. Let's just check theta equals 0. So what we get here is r minus L over 2 times 1 is greater than 0. Okay, so this one is stable if r is greater than L over 2. Okay, let's actually also note that that's a similar condition to what we had up here. This condition could be rewritten L less than 2r, or L over 2 less than r. Interesting. Okay. And unstable otherwise for this second solution. All right, now we know that we're not at the point theta, we're not at the point pi over 2, so we can divide by cos theta. So for the other, so otherwise, I can say r minus L over 2 is greater than r theta tan theta. I can divide by r, so let me do that. 1 minus L over 2r is greater than theta tan theta. Okay. So is that going to work? Well, in this case, I know what my theta equilibrium is. So maybe I should have subscripted this. This, we'll say that theta equilibrium solves this. Theta sub EQ solves this. So for theta equilibrium, I can stick in, for tan theta, my 2r over L theta equilibrium. So this is equal to theta equilibrium times, is it 2r over L or L over, yeah, 2r over L. Over L times theta equilibrium. Good. Okay, now a little bit of rearranging, and I get theta equilibrium squared is less than L over 2r, because I'm multiplying, minus L squared over quantity 2r squared. Okay, so if theta equilibrium ends up being less than this value, then the other point is stable, and if not, then it's not. I could also say this is L over 2r, 1 minus L over 2r. Okay. Now, let's think a little bit about the size of these things. Remember that r over 2L is 2r over L is greater than 1. This equation has an implication, which is that L over 2r is less than 1. So this thing is less than 1, and this whole quantity is also less than 1. Okay, so that is the condition for when this can happen. At least these two things are positive, so it's possible that theta equilibrium is that small. Since, as we could see when we looked in Mathematica, I can make theta equilibrium very small indeed. Okay, so there we go. There's an example of something that we can do using energy considerations that we couldn't do when we just used Newton's second law. Think about equilibrium and whether or not something admits equilibrium positions.